Hi, my name is Pablo Correa, and I will present to you my IceCube search for high-energy neutrinos from ultraluminous infrared galaxies. Getting right into it, ultraluminous infrared galaxies are the most luminous objects in the infrared sky. If we look at the electromagnetic spectrum of such an object, here on the right, you have this clear peak in the 8 to 1000 micron range of the infrared spectrum. And in fact, ultraluminous infrared galaxies are defined as objects with infrared luminosities exceeding 10 to the 12 solar luminosities in that waveband. If we look at the optical image of this particular galaxy, we see that it kind of resembles a toothbrush, hence the name toothbrush galaxy. The reason why it looks odd in this way is because it's a pair of interacting galaxies, which is a typical feature of ultraluminous infrared galaxies. Now, these objects are plausible sources of neutrinos, since they are mainly powered by starburst activity, and they can also have a contribution from an active galactic nucleus. In both these regions, you can have hadronic acceleration and hence neutrino production. So with that in mind, we made an object selection for an IceCube analysis. We started with an initial selection of 189 objects taken from 3 catalogs that are based on data of the infrared astronomical satellite. So the catalogs are given here in the bottom. With this initial selection, we then made an extra cut by determining the completeness of the sample. We found the redshift up to which we could observe all ULIRGs, giving the minimum luminosity of such an object, and given an iris sensitivity at 60 micron of 1 Jansky. And with these two things combined, we obtained a representative sample of 75 ultraluminous infrared galaxies within a redshift of 0.13. These 75 objects are shown here on the sky map on the bottom right. A quick recap of what IceCube actually is. It's an optical Cherenkov telescope that observes secondaries of neutrino interactions. The IceCube detector is located within the ice of the South Pole, and it contains over 5,000 optical modules, which are distributed over 86 strings within the ice of the South Pole. There's different signatures that can occur within the detector, but in this work we focus on muon tracks, which are produced in charged current interactions of muon neutrinos and anti-muon neutrinos. So what happens is when such a muon neutrino interacts with the ice inside or near the detector, it produces a muon. That muon will traverse the detector and leave behind this track-like signature, as you can see here on the bottom left. Such tracks have angular resolutions that are pretty good, less than a degree for muon energies larger than about a TV, and with that we can actually do neutrino astronomy. So that's why for this work we use the GFU data sample for the analysis. The GFU data sample consists of well-reconstructed tracks that were observed with IceCube with the full 86-string detector configuration between 2011 and 2018. It spans a lifetime of 7.5 years and contains roughly 1.5 million events. Now, the data sample is still dominated by atmospheric backgrounds. The main backgrounds for searches for sources of astrophysical neutrinos come from cosmic rays that interact with the atmosphere of the Earth and produce air showers. In the southern hemisphere, it's the muons produced in these air showers that are the main background. But in the northern hemisphere, the muons will not be able to traverse the Earth, so the main background is due to atmospheric neutrinos. The GFU data sample is already reduced to the 6.6 MHz all-sky rate, which is at the level of atmospheric neutrinos, but this is still several orders of magnitude higher than the astrophysical neutrino rate, and therefore we need to perform a statistical analysis in order to search for a possible small signal component in this background dominated dataset. The analysis method that we use is a maximum likelihood analysis. We use a time integrated unbent likelihood, which is given here on the bottom left, and what we fit for in the analysis is the number of astrophysical signal events, so the number of astrophysical neutrinos correlated with the ultraluminous infrared galaxies that we selected, and we also fit for a power law spectral index of this signal component. The likelihood here, you can see it has a signal term and a background term. The background term is spatially uniform in right ascension, and in energy it has a relatively soft E-3.7 power law spectrum. And the signal component spatially is assumed to follow a two-dimensional Gaussian centered around the location of an ultraluminous infrared galaxy, and energy-wise it's assumed to follow a power law spectrum for which we fit the spectral index. Now, the main thing about this likelihood is that we have this sum here. What we're doing is that we're stacking the sources in order to enhance the sensitivity of our search. So what we do is, instead of looking at each of these sources individually, we stack up their contribution and look at their combined neutrino emission in one go. That's the sum that you see here, and you have this weighting term where the weight depends on the detector response of the location of a certain source in the sky, and also depends on a theoretical weight which we choose to be the infrared flux of that source. Just as a nice analogy, you can think of stacking as instead of going to the store 3 separate times to buy each of the volumes of The Lord of the Rings separately, you can just stack it all up and go to the store one time and buy the combined edition in one go. So now we can look at the performance of the analysis. For that, we simulate pseudo signal according to this generic power law spectrum given here. What we plot here is the flux at 10 TeV as a function of spectral index of the pseudo signal. And the lines here show the sensitivity at 90% confidence level, the 3 sigma discovery potential, and the 5 sigma discovery potential. To make this a bit more intuitive, we can integrate the spectrum by convolving it over the effective area and integrating it over energy and the lifetime of the data sample. And that basically gives us the same plot here where we have the total number of ULIRG neutrinos is 7.5 years of GFU data as a function of the spectral index. And here the lines are indeed the same ones as shown in the previous plot. But now you can see that, for example, for an E-2 spectrum, we require about 10 neutrinos in order to see something in the data. That's our sensitivity. We see that this number increases for softer spectra. So we become less sensitive for softer spectra, which makes sense because then the signal component becomes harder to distinguish from the atmospheric background, which has a relatively soft energy spectrum. Okay, now we can look at the results of the analysis. These are shown here on the table on the right, and we basically fit a number of signal events that is equal to 0. So the spectral index remains undetermined, and the p-value of the analysis is equal to 1. So that means that the analysis is consistent with the background-only hypothesis, and we therefore set upper limits on the flux from our 75 ULIRGs, which are within a redshift of 0.13. And since we fit for 0 signal events, the upper limit is set equal to the sensitivity of the analysis. So basically we take the sensitivity, that's our flux limit of all ULIRGs up to a redshift of 0.13, and then we can extrapolate this to the flux of all ULIRGs up to a certain maximum redshift by taking into account this psi factor, which essentially integrates the redshift evolution of the sources over cosmic history. And the redshift evolution of ultraluminous infrared galaxies is given here, and it's a relatively strong redshift evolution. And in fact, these sources are pretty numerous, especially at redshift of about 1. Okay, now we can actually compare our results to the diffuse neutrino observations. In the next plots, we will always have flux as a function of energy, and the black data points in the red band indicate diffuse measurements made by IceCube. On the left plot here, we show integral limits for an E-2, E-2.5, and E-3 spectrum. In each case, we show the 90% central energy range that contributes to the upper limit. Now we can see that for an E-2 and E-2.5 spectrum, we are able to constrain the contribution of ultraluminous infrared galaxies to the diffuse neutrino observations. In addition, we can look at the quasi-differential limits on the plot on the right, and these are obtained by computing the E-2 upper limit in each bin of energy decade. And also here we see that we're able to constrain ultraluminous infrared galaxies as contributors to the diffuse observations, in particular in the energy bins of 10 to 100 TeV and 100 to 1000 TeV. Now we can also compare our results with model predictions. First, we will consider 2 cosmic ray reservoir models, where it's really the starburst component of the ultraluminous infrared galaxy that leads to neutrino production. And the first one is this model by He and others, where the neutrino flux is powered by hypernovae in ultraluminous infrared galaxies, and their prediction is shown here in the magenta line, which really falls on top of our E-2 upper limit. This means that we actually need a bit more data to be able to exclude or validate this model in particular. Next, we have the model by Palladino and others, and they consider a generic model of hadronically powered gamma ray galaxies, or HAGs. They're able to fit a large fraction of the diffuse neutrino observations with such a generic population, and what we find if we compare their prediction in the magenta line with our E-2.12 upper limit, we're able to exclude ultraluminous infrared galaxies as the sole HAGs that are responsible for the diffuse neutrino observations. So lastly, we can compare our results to the model by Verreken and others, where they consider the AGN inside the ULIRG as the main neutrino source. And in particular, their model considers the AGN to be Compton thick, so surrounded by very dense dust clouds, and the accelerated particles are dumped into this dense dust cloud, hence producing neutrinos. Now, this model depends strongly on this parameter Fe, which is the electron to proton luminosity ratio, or the inverse of the baryonic loading. So what we can do is fit this model to our E-2 flux upper limit from our ULIRG analysis and get an order of magnitude estimation of a lower limit on this Fe parameter. So we find that the electron to proton luminosity ratio should be larger than about 10 to the minus 3. This value is consistent with previous lower limits that were obtained in the context of an obscured AGN analysis that was also performed with IceCube. You can see those lower limits here on the right. This Fe parameter that we obtain is in the same ballpark as those found for this other analysis. And this brings me to the summary. We performed an IceCube stacking search for neutrinos from ultraluminous infrared galaxies, but unfortunately, we did not identify any astrophysical signal in the data. We therefore set upper limits on the contribution of the ULIRG source population to the diffuse neutrino observations, and we were also able to constrain model predictions. We also submitted a paper with these results to the archive recently, so if you're interested in more details, please feel free to check it out. Now for the future, we might consider luminous infrared galaxies as candidate neutrino sources, which are the less luminous but more numerous siblings of the ultraluminous infrared galaxies. And on the other hand, we might also consider Compton thick AGN as candidate neutrino sources, in particular because these are possible gamma ray dim neutrino sources, which is something that is hinted towards by the diffuse gamma ray neutrino observations. And this is something that people are looking into in IceCube. You can see these proceedings here if you're interested in that. But with this, I would like to thank you for watching and have a nice day. Take care. Bye.